All right. I hope you guys are doing well today. We are going to be talking about two topics that are going to seem like they are completely unrelated to each other, but we'll find out during Monday's class when we start applying what we're learning today to circuits that they are actually very much related. So the first topic that I want to talk about today is a review of complex numbers. I say that it is a review. That being said, I'm genuinely not sure if complex numbers are actually taught in your pre-calculus classes, so this might be your first exposure to them. So, does anybody have any idea what a complex number might be? Any thoughts?
Are these the numbers with like attached to them? Or is those
Yeah.
imaginary?
So the numbers with I attached to them are imaginary numbers. That being said, a complex number is nothing more than a combination of a real number and an imaginary number. So you were half correct. Okay. So there are multiple different ways that we can represent complex numbers, and we are going to talk about all of them today, but we're going to largely focus on the two that are used most by engineers. So the first thing that I'm going to do is I'm going to put a complex plane in the middle of the screen here. So our vertical axis is going to be our imaginary axis. And our horizontal axis, what the crap is going on, is going to be our real axis. So we can think about this as if it were two number lines, right? So the standard number line that we learned in elementary school is our real axis, where everything to the left of zero represents negative numbers, and everything to the right of zero represents positive numbers. Well, we have a second number line that is just rotated 90 degrees out of phase with our real axis, and that's our imaginary number line, where everything above the horizontal axis is going to represent positive imaginary numbers, and everything below the horizontal axis is going to represent negative imaginary numbers. So I am going to draw an arbitrary complex number on our complex plane here. So something akin to this. Okay. So I'm going to call this complex number A, and I'm going to denote that it is a complex number by putting a bar over the top of it. In textbooks and stuff like that, they may use a bar, but more regularly, they will use boldface type to represent complex numbers, but I can't write in bold, so I use the bar notation to identify a complex number. Okay. So the first form of complex number that we're going to talk about is the rectangular form. Okay. So what I'm going to do is I'm going to essentially draw a projection of this complex number onto the real axis, and I'm going to draw a projection of this complex number onto the imaginary axis like so. And I'm going to call this real part lowercase a, and I'm going to call this imaginary part lowercase b. So we could represent this complex number a in rectangular form as a plus jb, where this part a right here represents the real part of complex number a, and b right here represents the imaginary part of complex number A. Now, some of you may be asking yourselves, what the hell is J? We've never heard of that before, and that's perfectly fair. Okay. So in your math classes and things like that, you probably learned that the imaginary operator I was equal to the square root of -1. That is 100% true, but we don't use I to represent the square root of -1 in electrical engineering because we use it so often to refer to currents. So instead, we have adopted using a lowercase j to represent the imaginary operator, the square root of -1. So I'm going to use j everywhere you guys would have used I in your prior math classes and stuff like that. Are we all okay with that?
Yeah.
Okay. So what I'm going to do now is just for the hell of it, I'm going to develop a little table down here because this might be useful to us. So this is probably more spots than we need, but that'll be fine. So the first thing I'm going to do is I'm going to put j to the first power here. So j to the first power is just j by itself, and we know that is the square root of 1. So j to the second power is just going to be the square root of 1 quantity squared, which is -1. J to the third power is just j to the 1 times j to the 2. So that's going to be the same thing as negative the square root of -1, or negative j. J to the fourth power is going to be j squared times j squared, or -1 times -1 is +1. And then j to the fifth is j to the fourth times j to the 1, which is the same thing as j. So we can see that it's just going to cycle over and over and over again. So like j to the 6 is the same thing as j to the 2, j to the 7 is the same thing as j to the 3, and so on and so forth. We can go the other direction as well. So we could say that j to the 0, well, anything to the 0th power is just 1, right? Well, j to the -1 is 1 over j, which is 1 over the square root of -1. So I could multiply this by, let's see, the square root of -1 over the square root of -1. And so that would give me a square root of -1 in the numerator, which is just j, and then -1 in the denominator. So this is going to look like minus j. J to the -2 is 1 over j squared. Well, j squared is -1, so that's just 1 over -1 is -1. J to the -3 is just j to the -2 times j to the -1. So that is -1 times -j is positive j. And j to the -4 is j to the -2 times j to the -2, which is -1 times -1, which is +1. And we can see that, again, that cycle just continues. So if j to the -3 is the same thing as j to the 1, is the same thing as j to the 5, is the same thing as j to the 9, et cetera, et cetera, et cetera. The reason why I'm bringing this up is because a lot of you guys' calculators can only handle j to the +or-3. So some calculators that you guys have, if you put in j to the fourth power, it won't know what the hell to do. So what you would do is just subtract 4 from that index to bring it down to something that your calculator can handle. Similarly, if you had j to the minus 6, you could add 4 to that index, making it j to the minus 2, and your calculator could be able to handle that. So essentially, it's just these 4 values repeating over and over and over again. And if your calculator gives you a math error, just continue to add or subtract 4 until it doesn't. Okay. All right. So this is our, sorry, getting back to actual complex numbers instead of just imaginary numbers. We have our rectangular form here, where once again, lowercase a is the real part of our complex number a, and lowercase b, without the j, I want to be very clear about that, is the imaginary part of our complex number a. So now I'm going to talk about the exponential form. And over here on the far right, the polar form. And I'm throwing these two guys on the same side of the graph because they use the exact same information. They just represent it in slightly different ways. So in truth, the polar form of a complex number is actually just an engineering shorthand of the exponential form, okay? So I'm going to start by showing you what the exponential form of a complex number looks like. So in order to do that, I'm going to define a couple of things here. Okay? So I'm going to say that the length of this vector, that is my complex number A, is going to be A with absolute value signs around it. And what I mean by that is just the magnitude of that vector, okay? And our complex number A also forms some angle with the real axis where we are measuring, the real axis would count as 0 degrees or 0 radians if we were so inclined. And we are going to measure counterclockwise until we hit our complex number vector there. And I'm going to call this angle theta A, okay? So in exponential form, we could say that our complex number A is given by the magnitude of A, which is just the length of the complex number, multiplied by a factor of e to the j times theta A. So that is our exponential form. So the information that's buried inside of it is the length or the magnitude of the complex number, as well as the angle formed with the real axis. And then our polar form representation, which is again just a shorthand notation for the exponential form, is going to be the magnitude of a angle. So that's just an angle operator, theta A. Those two representations, exponential and polar, contain the exact same information. In electrical engineering, we use polar form the overwhelming majority of the time. Hardly ever use exponential form except for a few derivations, which I'm going to wind up doing in probably our next class meeting. But anyway. One thing that I want to point out, I'm going to say this, it is being recorded, but I understand that probably somewhere between 1/3 and 1/2 of you are going to completely forget about this in 10 minutes. This rectangular form right here and this polar form right here are what your calculator can handle. If you try to put an exponential form complex number into your calculator or into MathCAD or anything like that, it is not going to know what the hell to do with it. So anytime you are given an exponential form complex number in this class, you should just immediately convert it into polar form by keeping the magnitude, keeping the angle, and throwing everything else away. Okay, so exponential form cannot be interpreted by your calculators or MathCAD to my knowledge. So just to be real clear about that. Okay. So before we move on to discuss how we convert between these two forms and things like that, does anybody have any questions? All right, so let's talk about how to convert from rectangular form into polar or exponential form, okay? So I'm going to start by giving you a definition for the magnitude of our complex number A. So essentially, we have, if we look at our complex plane representation of complex number a right triangle, and the magnitude is just the hypotenuse of that right triangle. So we can use good old Pythagorean's theorem in order to determine the length of this complex number. So it's simply going to be the square root of a squared plus b squared, which I can generalize to be the square root of the real part of complex number a, quantity squared, plus the imaginary part of complex number a, quantity squared. So that's how I get my magnitude if I know my rectangular components, okay? For my angle, there is a couple of different ways that it could be done, all using trig identities. But by far the most common definition that I've seen in textbooks and things like that defines our angle theta A as the arctangent or inverse tangent of B over A, or more generically, the arctangent of the imaginary part of A divided by the real part of A. So that's how we can determine our polar form or exponential form components from our rectangular form. If we want to go in the opposite direction, it's not particularly difficult. So we could say that A, which is just the real part of complex number A, is going to be the magnitude of our complex number times the cosine of our angle. And similarly, we could say that B, is nothing more than the imaginary part of complex number A. And that is going to be the magnitude of A times the sine of our angle. So before we look at an example that seems like it's breaking this, does anybody have any questions, comments, or concerns? All right, so what I would like for us to do is to do a transformation from rectangular form into polar form by hand. And I'm telling you right now, it's going to give us an answer that doesn't make sense, okay? So let's come down here. And let's say that I have some complex number x that is -3 plus j5, okay? And I want to figure out what this looks like in polar form. So we're going to convert this to polar form. So this is a two-step process. The first thing we have to figure out is what the magnitude of x is going to be. So that's simply going to be the square root of -3 quantity squared plus 5 quantity squared. And so if I throw that into my calculator, I wound up getting the square root of 34. If any of you guys are following along with your calculator and you got something different, please let me know, but I think we should all be pretty okay with that. For the angle, theta x, I'm going to enter into my calculator exactly the definition that I told you guys a moment ago. So that's going to be the arctangent of our imaginary part, which is +5, over our real part, which is -3. And when I do that, I get an angle of -59.036 degrees. So if I put these two parts together, I could say that the polar form of our complex number x, and I'm going to put a question mark here, is going to be the square root of 34 with an angle of -59.036 degrees. So that result is actually incorrect, okay? And I'd like to explain why it's incorrect. So if I were to plot that number on a complex plane, where this is my positive imaginary axis, and this is my positive real axis, square root of 34, angle -59.036 would be something in the ballpark of down here. So I have something that appears like it is in the fourth quadrant of this complex plane. Well, if I plot this guy in rectangular form, I would go -3 units in the real direction, +5 units in the imaginary direction. So I got this length really long just because I don't know what the hell the square root of 34 is off the top of my head. But it should actually be something up here in quadrant 2. Okay. So this is where x really lies based on the rectangular coordinates that we started from, but we were accidentally given something in the fourth quadrant. Can anybody think of why that happened? All right, so I guess I'm just going to tell you guys. So why that happened is because, well, really there's two reasons, and they're related to each other. So your calculator, when it performs the arctangent operation, is always going to give you an angle that lies in either quadrant 1 or quadrant 4. So somewhere between -90 degrees and +90 degrees, okay? The reason why it does that is because it can't tell the difference between if I have a negative sign in the numerator of my fraction or a negative sign in the denominator. So if I put in the arctangent of -5 over +3, it's going to spit out that exact same answer of -59.036 degrees. So realistically, all we would have to do to correct this is just add 180 degrees to the angle that we got, which would then force it up into quadrant 2, which is where we know it should be. However, if I'm being blunt here, that's a huge pain in the ass. So instead, we are pretty much never going to do conversion of rectangular form complex numbers into polar form complex numbers by hand, because if we use the complex settings on our calculator, it can handle that for us without us ever having to think about, should this number be in the first quadrant, the fourth quadrant, third quadrant, second quadrant, etc. So what I'm going to do is I'm going to move my little TI calculator thing over to the screen. I can describe how to do this for those of you that have Casios, but for whatever reason, their license server that would allow me to purchase a license for their emulator isn't working today. So I don't know when it's going to be up. If you look at my video from last summer, I should have some stuff about using the Casio calculators on that one. But again, I'd be more than happy to describe it to you all if that is helpful if you have TIs, or excuse me, if you have Casios. But for the TI folks, I can literally just show you. So what I'm going to do is I'm going to type in our complex number here. So -3 plus 5. And then to get my imaginary operator, I'm going to press this pi button 3 times. So if I press it once, it gives me pi. If I press it again, it gives me e. And if I press it a third time, it gives me I, which is the imaginary operator that we're interested in. Then I'm going to press second and the pi button, and that's going to bring up my complex menu. I'm just going to scroll down here to option 4, where this is the button that literally just converts whatever the hell I have on my screen into polar form. So I'm going to press the 4 key here, and I'm going to press enter, and I wound up getting the square root of 34, which is the magnitude that we got, and then positive 120.964 degrees. I'd be willing to bet an extraordinarily large sum of money that if I put negative 59.036 degrees plus 180 degrees into my calculator, I will get this 120.963 whatever. Okay. So that's how you use a TI calculator to convert from rectangular form into polar form. If we wanted to do the opposite, if we go back to that complex menu and we keep scrolling down here, option 5 is for converting polar form complex numbers back into rectangular form complex numbers. Okay. So Trevor asked, is there a reason why his calculator gives him a decimal and not a square root? So if I clear this and I press this button right here, shit. Um, let me do something else really quickly. So one thing that I want to mention to you guys is that the overwhelming majority of the time we're going to be dealing with current and voltage signals, and those are typically expressed in polar form. So you might want to go into the mode of your calculator and change it from default, which would put your answer in rectangular form, and change the default to polar form, like so. So if I press enter with this guy moused over, and I press clear, if I just put that minus, uh, damn it, I'm using the wrong minus sign. Where the hell's the correct one? There we go. -3 plus 5 I, and now I press enter, it automatically spits it out. Now, if I press this button, why is it? I would expect that button to give me the decimal. That's what it does on my physical calculator. So now it's giving me that. So it might just be your setting, but realistically, it doesn't particularly matter which way your calculator gives you the answer. If it gives it to you in a square root, you should be able to just press this button right here, which would convert it into a decimal form. On your exams, I will always give you the answer expressed in a decimal form out to 3 decimal places like I've done for everything else. So let me change that back because it's going to bother me that it has the e to the 0 bit. Okay. So anybody with a Casio that's paying attention, would they care to have me explain how to do it with their calculator, or are you guys good to figure it out or watch my video from last summer? All right, well, nobody's saying anything, so either you've all got TIs, you all already know how to do it, or you just don't give a shit, which is perfectly reasonable. So what I would like for you guys to do is take a moment to familiarize yourself with how to use your calculator by converting these complex numbers into from rectangular form into polar form. I understand wholeheartedly that you're doing none of this work by hand. So you realistically, what I'm expecting of you when you turn in at least the work for this part of the in-class assignment is pretty much just giving me exactly the answers that I have written down. But I really would prefer if you guys actually learned to use your calculators to handle this complex number stuff, because we're going to be doing a ridiculous amount of it for the remainder of the class. For what it's worth, problem 2 is just doing that conversion in the opposite direction. I do want to point out something to you all, though. If we look at this guy right here, there is no degree sign. So that means that this number is an exponential form complex number, and its angle is expressed in radians. So I'm going to bring my calculator up, and I'm going to show you guys how I would approach this one. Let's scroll up here so we can see it. So if I clear all this gobbledygook out, I probably overuse parentheses, but I prefer to use them. So I would do 61.2. The angle operator I get by pressing second and then the pi key to bring up the complex menu, and then it's option 1. I'm going to open another parentheses here. So my angle is negative 1.939 in radians. We can see that my calculator is in degree mode. So what I'm going to do is I'm going to multiply this number by a factor of 180 over pi, and that's converting it into decimal form for me. And so now, closing those parentheses, and when I press enter, it's going to give me this answer in polar form, which is just the same number with the angle expressed in degrees. And now I can do answer second complex and then option 5 to convert it to rectangular. And I get negative 22.028 and some change minus 57.098 and some change if I scroll all the way far enough. So it absolutely gave me the rectangular form that I was looking for. All right. So before we move on to mathematical operations using complex numbers, does anybody have any questions? All right. So We're going to start with the conjugate operation, which is unique to complex numbers. Okay. So if I have a complex number, a is equal to lowercase a plus jb in rectangular form, then a conjugate, and I'm going to denote the conjugate operation with an asterisk here, is simply going to be a minus jb. So in rectangular form, the conjugate operation simply converts or flips the sign on the imaginary part of our complex number. Okay. So if I were to look at this on a complex plane, where here's my positive real axis, here's my imaginary axis, if this guy right here is A, where this is the real part and this is the imaginary part, then A conjugate is just going to be this guy down here, where the real part is the same, but the imaginary part is now at negative B. So in exponential or polar form, my complex number A, magnitude A e to the j theta A, or magnitude A angle theta A. Can anybody think about what the complex conjugate operation might do for this particular form of our complex numbers? So I've already drawn it on the screen here, so hopefully we can sort things out. So if this angle right here is theta A, what angle is the one below the horizontal axis?
Negative theta A.
Exactly right. It's literally just negative theta A. So essentially, the complex conjugate operation just flips the sign on the angle if we have an exponential form complex number or a polar form complex number. So our magnitude stays the same, but now we're going to have e to the negative j theta A, or the magnitude of A with an angle of negative theta A. So that's the conjugate operation. For what it's worth, if you just can't remember that or you find it too confusing, your calculator can totally do it for you. For those of you that have a TI, you access the conjugate operation by pressing second and then pi. That's where all of your complex number operations are that aren't just basic addition, subtraction, multiplication, division, etc. And scroll down to option 6, and it literally says conjugate. So if I have, I'm going to press this guy right here. So the conjugate of 5 minus 3i, it should give me 5 plus 3i in rectangular form. I'm going to force it to give me that result in rectangular form like so. And exactly what I said, it just flips the sign on the imaginary part. Okay, any questions about the complex conjugate operation? All right, so we'll move on to bigger and better things. So let's go down here. So let's talk about addition first. And again, I 100% expect you guys to do this in your calculator, but it is kind of useful to at least understand what's going on if you are ever needed to do it by hand or think about things that are going on. So if we have some complex number that is equal to a plus jb, and a second complex number b that is equal to c plus jd, if I want to add these two complex numbers together, essentially it's going to work like how you add vectors together in your physics classes. You're going to add your real components together and you're going to add your imaginary components together. So this would look like a plus jb plus c plus jd is going to give us a real part of a plus c plus an imaginary part of b plus d. So you add the real parts together and you add the imaginary parts together. That's it. So there's addition. There is not an easy way to do addition using polar form or exponential form complex numbers. So I'm just going to leave it with this rectangular explanation and we'll call it a day. Subtraction is literally just addition with a negative sign. So if I use those same complex numbers, a plus jb, and b is equal to c plus jd, excuse me, then complex number a minus complex number b is going to look like a plus jb minus c plus jd. So I'm going to have as a real part a minus c plus j, and then as an imaginary part b minus d. So works exactly like addition, except that there's a negative sign. Okay. Just like subtraction, there is no easy way to do, or excuse me, just like addition, there's no easy way to do subtraction using polar form or exponential form complex numbers. So I'm going to leave this as is. Now let's get into multiplication. So once again, having a complex number a is equal to a plus jb, and a complex number b is equal to c plus jd. If I want to multiply these two numbers together, I'm going to write that as complex number a beside complex number b. Okay? So let me talk about this just briefly. It's going to seem like a rant, and it's not a rant, but there's a reason why I don't use a multiplication sign here. Okay. So usually when we think about multiplying two numbers together, we might have something like a times b. Well, the reason why I don't want to use that is because it could easily be confused with the cross product vector operation, which does not exist for complex numbers, right? So I have two-dimensional numbers, two-dimensional complex numbers. So there's a real part and an imaginary part. Cross product does not exist, so I don't want to confuse you with that. Just like Joseph said, I also can't put a dot in the middle because you could too easily confuse that with a dot product, which also does not exist for complex numbers. I can't use an asterisk because that's the sign that I use for the conjugate operation. So the only way that I can denote that I am multiplying two complex numbers together is literally by putting them next to each other, which is what I do. So this is going to look like a plus jb multiplied by c plus jd. And so I'm just going to FOIL this out like we learned in junior high or whatever. So I'm going to have a times c plus j a times d plus j b times c plus j squared b times d. Does anybody remember what j squared is from earlier? And if you don't remember, scroll up and look it up in the table.
-1.
-1. So this actually simplifies to a real part of AC minus BD plus an imaginary part of AD plus BC. So that is multiplication using rectangular form complex numbers, and it isn't crazy difficult by any stretch of the imagination, but it is a little bit tedious. Okay. So let's look at what happens if we were to use exponential form complex numbers instead. So if I represent my complex number A as the magnitude of A, e to the j theta A, and complex number B as the magnitude of B, e to the j theta B, well, when I multiply these guys together, I'm going to have magnitude of A, e to the j theta A, times the magnitude of B, e to the j theta B. Well, my magnitudes are going to multiply, so I'll have magnitude of A multiplied by magnitude of B. What's e to the j theta A times e to the j theta B? So what happens when I multiply two exponential functions? Joseph's exactly right. The arguments of the exponential functions add. So that's going to look like e to the j theta A plus theta B. And in polar form, this would look like the magnitude of A times the magnitude of B with an angle of theta A plus theta B. So by hand, multiplication is actually way easier to do using polar form complex numbers than rectangular form complex numbers because you just multiply the magnitudes and add the angles. Okay. Now let's talk about division. Division is a bit of a pain in the ass in rectangular form. So I'm mainly showing this to you guys in order to show you an identity that I'm going to use a couple of times throughout this class. So starting again with our complex numbers, A plus JB and C plus JD, A divided by B, and I'm leaving a space there on purpose, is going to look like A plus JB divided by C plus JD. Now, there's technically nothing wrong with this. However, the form of our answer doesn't look like anything that we've gotten before. So I'm going to scroll up here and I want to just talk through things really quickly. So when we added complex numbers together in rectangular form, our result had a real part and an imaginary part. When we subtracted complex numbers, our result had a real part and an imaginary part. When we multiplied complex numbers, our result had a real part and an imaginary part. But when we do this simple division, we don't have an easily identifiable real part and an imaginary part. In order to force our result to give us a real part and an imaginary part, we have to get a little creative. So what I'm going to do here is I'm going to multiply by the conjugate of the denominator over the conjugate of the denominator. So that's just a fancy representation of the number 1. Okay. So over here on the right, I'm going to put C minus JD over C minus JD, because recall that the complex conjugate of a rectangular form complex number simply changes the sign on the imaginary part. And now I'm going to FOIL this stuff out. So in our numerator, we're going to have A times C minus J, A times D, plus J, B times C, and then minus J squared, B times D. And in my denominator, I'm going to have c times c, which I'm going to write as c squared, minus j cd plus j cd minus j squared d squared. Well, from our table, we know that whenever we see a j squared, that's -1. So whenever we see a minus j squared, that should just be +1. So that means in our numerator, we're going to have AC plus BD plus J times BC minus AD, all divided by C squared plus D squared. And to make this very obvious about what the real part and the imaginary part is, I can write this as AC plus BD over C squared plus D squared plus J BC minus AD over C squared plus D squared. So let's talk about what multiplying by the conjugate did there. It essentially got rid of all of the complex numbers in our denominator. So generally speaking, and I'll just sneak this in down here, if I have a complex number A is equal to A plus JB, and the conjugate of A is A minus JB, then when I multiply A conjugate times A, that's going to look like A plus JB times A minus JB, or A squared plus B squared is just the magnitude of A squared. So anytime I multiply a complex number by its own complex conjugate, it just looks like the magnitude of that complex number squared. We are going to see that pop up several times, so I just wanted to make you guys aware of it. All right. So now let's look at what happens if we use exponential form complex numbers. So, excuse me. If we have A is equal to the magnitude of A, e to the j theta A, and B is equal to the magnitude of B, e to the j theta B, then A over B is going to look like the magnitude of A, e to the j theta A, over the magnitude of B, e to the j theta B, which is just the magnitude of A divided by the magnitude of B, e to the j theta A minus theta B. And in polar form, that would be the magnitude of A over the magnitude of B with an angle of theta A minus theta B. So essentially, using polar form complex numbers, division is just divide the magnitudes and take the difference of the angles. So it is way easier to do division in polar form or exponential form than it is to do it in rectangular form. Okay, so now let's pop over here to the ICA again, and let's scroll down to part 3. So problem 3 is all about just performing those mathematical operations, okay? So I have defined 3 different rectangular form complex numbers, and I'm asking you guys to perform these various operations. And again, I'm just expecting you to use your calculator, okay? So I'm going to walk you through part of this problem. So I'll let you guys pick if you want me to work part A, part B, or part C. Just first one to say anything wins. Jaime says part C. Sounds great. So what I'm going to do is I'm going to store these things in my calculator to make my life easier. Okay. So I'm going to do -2 plus 6 pi to give me I. I'm going to press store X and then enter. And now that is stored in my calculator as X. It converted it over to polar form, but that doesn't matter to me at all because the calculator literally doesn't care. Okay. 4 plus 7 I'm going to store that as Y. And -6 minus 5 I'm going to store that as Z. So for part C, we are asked to compute j to the 7th power multiplied by x conjugate plus z. So if I do 1i to the 7th power, I believe this calculator is going to freak out. Yep, it gives me a domain error. Okay. So instead, what I can do is I can just subtract 4 from that index. So 1i to the 3rd power is the same thing as 1i to the 7th power. And if I press enter here, it gives me a result. So that's how I'm going to take care of that part. So 1i to the 3rd power multiplied by the conjugate of x plus z gives me 3 square root of 17, with an angle of 194.036. If I press this button, it's still not doing what I want it to do. Let me go back into mode here. (1.2369) times 10 to the 1 is the 12.369. So that part is correct. The angle it gave me is, God, it does it with the angle too. That's horrifying. Negative 165.964 degrees. So the answer that I provided you right here is 194.036 degrees. So why did I get something different? Well, your calculator is always going to give you a result that is somewhere between negative 180 degrees and positive 180 degrees. But here in the problem statement, I say that I want the smallest possible positive angle. So how I'm going to fix that part is I'm going to do so I'm going to press second in complex. I'm going to choose option 2, which is going to return the polar angle of whatever I'm interested in. So the polar angle of my previous answer plus 360 degrees. So that's going to move myself around this unit circle in a counterclockwise direction, and it's going to give me the positive angle that I'm looking for, 194.036, where that e to the 2 thing just means that's 1.94 times 10 to the 2 is the 194 we're interested in. Okay. So storing complex numbers in your calculators is a fantastic way to approach all of this kind of stuff, because it doesn't lead to rounding errors and it lets you manipulate things further. So I would highly encourage you guys to learn how to store information in your calculator. It will be a lifesaver for what we're doing for the remainder of the class. Okay. Before we move on to the second part of this lecture, which is a review of sinusoidal signals, does anybody have any questions about the complex number stuff, how to use your calculators, etc.? I'm still frustrated that this dumb thing won't just give me a decimal form without this scientific notation crap. What happens if I put it in engineering form? Let me just see something here. Yeah, I don't know why this emulated calculator only gives me the magnitude, like it won't give me a decimal version of the magnitude. That's weird, but it is what it is. Okay, well, I didn't see anybody ask any questions in the chat. I didn't hear anybody ask any questions, so I assume you guys are okay. And we'll move on to our next topic of the day. So this is going to be our review of sinusoidal signals. I'm going to pre-apologize for my inability to draw a sine wave to save my damn life, but I'm going to do my best here. So let's say that I have some sinusoidal signal like so. So on my vertical axis is just going to be the value of x of t, and on my horizontal axis, this is going to be t. I'm going to draw a signal here. Like so. Hopefully that's not too shitty for you guys. And now I am going to describe this function using math. So we could either describe this particular signal as a sine function or a cosine function. So I'm going to actually describe it as both. So as a sine function, this might be something like x sub naught, I'll talk about what that part means in a moment, times the sine of omega t plus some phase angle theta. Or as a cosine function, we might write it as x sub naught cosine omega t plus some phase angle phi, where I have intentionally used a different Greek letter for the phase angle of the sine function and the phase angle of the cosine function, because they are literally going to be different numbers, okay? So what I want us to do over the next couple of minutes, or I guess what I'm going to do over the next couple of minutes, is hopefully relay you guys enough information to where you can understand how we might get the magnitude, angular frequency, and phase angle from our plot. And then also I'm going to describe what those things are. So I'm going to start with the magnitude, okay? So x naught is the magnitude or amplitude of the sinusoidal signal. Goodness, that looks shitty. Okay. Representing its peak value. So on our graph, this distance from the peak of this curve down to the horizontal axis is x naught. Now, as it turns out, the distance from the horizontal axis down to the most negative value is also x naught, okay? So this first term is just essentially a scaling factor. So if I had 1 sine omega t plus theta, that means that I would have a signal that is 1 unit tall. So it's oscillating between plus and minus 1, essentially, at a particular angular frequency and with a particular phase angle, okay? So x naught is just the height of the sinusoidal signal measured from the horizontal axis. Are we all relatively okay with that? All right. So now let's talk about omega. So I'm going to describe omega first, and then I'm going to talk about a couple of other things, and we'll tie it back to how we can actually find it from our graph if we were so inclined. Okay. So omega is the angular frequency of the sinusoid. And it represents how quickly the signal oscillates. Okay. It is always measured with units of radians per second. Okay. So if we have a signal with a large value of omega, it means that it changes from its peak value to its negative peak value very quickly. If it has a very small value of omega, it changes from its peak value to its negative peak value very slowly. Okay. So let me pull Desmos over here really quickly so we can look at something. Okay. So hopefully you guys can all see this. So I've just put in a generic function here, 10 cosine 3x plus 22. So 10 is the amplitude, which we've already talked about. 3 in this case is the angular frequency. X is just our variable. And then this 22 times pi over 180, that's our phase angle, which we haven't talked about just yet. And that's just me converting it into radians because the default setting for this graphing calculator thing online is in radians. So if we compare that to a signal that is 10 cosine, let's just do 1x plus 22 times pi over 180 so that everything is exactly the same except our angular frequency. And let's kind of zoom out on this. So let's make it go from -5 to +5 here. We can see that the signal with the angular frequency of 1 radian per second takes a lot longer to go from its negative peak to the next time it hits a negative peak, whereas the red signal, which has an angular frequency of 3 radians per second, does it much faster, right? So the larger the value of omega, the more quickly our signal oscillates, as I mentioned a moment ago. Okay. All right. So now let's refer this to things that we can actually measure. Okay. So if I look on my graph here, the distance between these positive peaks is what I'm going to call the frequency, excuse me, the period of my signal. So let me just make a note here. T is the period of the sinusoidal signal. And it represents the time needed for one full cycle to occur. So I've chosen to represent this full cycle as the amount of time that elapses between when I hit my positive peak value. If I had drawn more of the signal, I might define my period as the amount of time between the negative peaks or the amount of time between the zero crossings or something like that. So the period just represents how long we need to wait until the signal repeats itself, okay? Well, the period is essentially the amount of time per cycle. So if we take the inverse of that, we wind up getting the frequency f, okay? So f is the linear frequency of the sinusoidal signal. And it represents the number of cycles that occur in a given amount of time. Usually 1 second. So I'm going to say that frequency is typically measured in what are called hertz. So that's Hz, and that is literally just the inverse of a second. So if period is the amount of time per cycle, frequency is the number of cycles per time. So they are literally the inverse of each other. So we can say that T is equal to 1 over F, or transversely, F is equal to 1 over T. Now let's tie this back to our angular frequency. So every cycle represents the angle of our signal changing by 2 pi radians. So our angular frequency, omega, is nothing more than 2 pi radians times our linear frequency f. Or we could write this as 2 pi divided by the period of our signal. So if our signal that I drew up here, if we had put numbers or anything, if we can figure out how long the period is, we can use that to back calculate what our angular frequency is. So that's how all three of those quantities are related. The ones that I'm most interested in you understanding are the relationship between period and angular frequency, because we don't really deal with linear frequency a lot in this class, at least not until we start looking at single phase power systems at the very end. Okay. So the last part of our mathematical expression that we have to deal with is the phase angle, okay? So theta, that's a shitty looking theta, and phi, are the phase angles for our sinusoidal signals. And they represent how much our signal is shifted in time. So let me explain what I mean by shifted in time. So I'm going to ask you guys a question. I would appreciate if one of you would answer it. If I just have the signal sine of omega t, no phase angle or anything like that, right? At what value of t is my signal equal to 0? So for what value of t is sine of t 0? So pi is one of them for sure. What's another one, Gustavo? 0. So 0 is the one that I was actually looking for. Thank you, Trevor. But Gustavo is correct. Actually, any integer multiple of pi will cause the sine function to be 0, but I was really interested in the one that's actually occurring at 0. So essentially, if we look at this graph here and we're treating it as if it were a sine function, it is actually advanced by some small amount of time here that I'm going to call theta t, or excuse me, delta t sub 1, okay? So because my signal is 0 and increasing at a time before t is equal to 0, we would consider this signal to be advanced in time. Now, if I'm looking at it as a sine function, well, at t is equal to 0, I expect, excuse me, as a cosine function, at t is equal to 0, I would expect my cosine function to be at its maximum value. So we could think of that as this amount of time would be some delta t2, representing how much our cosine signal is delayed because its peak value is occurring at a later time than t is equal to 0. So our phase angle is related to this amount of time shift that our signal is experiencing. And we'll play around with things with Desmos here in just a minute, just to make sure we're all catching the same thing here. So let's come down here and let's say that positive phase angles occur when our signal is advanced in time. And I'm going to put down here in parentheses, shifted to the left. Okay. And that phase angle, I'm just going to do it in terms of theta, is going to look like omega times the amount of time shift that has occurred. Okay. Negative phase angles occur when our signal is delayed in time. Or shifted to the right. And in this case, our phase angle, generically using theta again, is just going to be negative omega times our delta t. Okay. So I'm going to pull Desmos over here, if my computer will let me. Let's clear these guys out. So let's just have our first signal f1 of x is going to be 5 You guys want a sine function or a cosine function?
Cosine.
Cosine. All right. I'm going to do an angular frequency of 6t, and I'm just, or excuse me, 6 radians per second, and I'm just going to leave that alone, right? So this is our signal with no phase angle whatsoever. Now, I'm going to add a phase angle of 15 degrees. So 15 times pi over 180. So we can see that our positive phase angle gives us a small amount of shift to the left because we're only shifting it by the phase by 15 degrees. But if I shifted this by 105 degrees, it's a much larger shift to the left. So the larger that that phase angle is while it's positive just means that I'm shifting to the left more and more and more. Similarly, if I put in a negative phase angle, let's start with something small like 15 degrees again. Now my red curve is shifted slightly to the right. Okay, so it is delayed in time. And if I make this, let's say 75 degrees, it shifted even further to the right. So it's delayed even more, okay? So it's always seemed counterintuitive to me, but positive phase angles are definitely shifts to the left, and negative phase angles are definitely shifts to the right. So the way that I keep that correct in my head is by putting things in terms of advanced or delayed. So advanced in time means that things are occurring before t is equal to 0, and delayed in time means that things are occurring after t is equal to 0. Okay. All right, so do we have a reasonable grasp on the magnitude of a sinusoidal signal, the angular frequency omega of a sinusoidal signal, and the phase angle of a sinusoidal signal? We know what those things are loosely. So if so, I'd like for us to work one of the in-class assignment problems together. This is very similar to a homework problem from set number 19. And so, yeah, I just want to work it with you because it is surprising what we can come up with how little information was actually provided, okay? So if we scroll down here to problem 4, we are told that we have a sine wave and that it is 0 and increasing at t is equal to 9.8 milliseconds, and the succeeding positive maximum of 14.9 occurs at t is equal to 15.1 milliseconds. Using that very small amount of information, we are expected to be able to come up with a mathematical expression that describes f of t in the form specifically where we know what the magnitude is, we know what the angular frequency is, and we know what the phase angle is, okay? So how I like to approach this problem whenever you guys ask me about it when you're struggling with your homework is by drawing a picture, okay? So at t is equal to 9.8 seconds, so I'm just going to put, excuse me, 9.8 milliseconds is right here. We are told that our signal is 0, but that it is increasing, okay? And then at 15.1 milliseconds, so over here, it hits its maximum of 14.9. So we have something like this. And over here, this represents 14.9. So I'm going to ask you guys a couple of questions here really quickly. Since 14.9 whatever is the maximum, what is the magnitude of our signal? 14.9, exactly right. So the magnitude of our signal is its peak value. We talked about that a little while ago. So the F naught that we are looking for is literally just 14.9. So there is a reason that this number is the same as this number, okay? So we were told what the magnitude of our signal is. Now let's figure out what omega is, okay? So that description that we were given essentially tells us what's going on in 1/4 of a sine wave, right? So if we go from when it is 0 to when it hits its peak value, we've looked at 1/4 of a sine wave. And just to prove that to you really quickly, let me pull up that Desmos thing again if I didn't exit out. Yeah, let me click this thing off, right? So we're 0 at this particular point in time and increasing, and then we hit our maximum here. So this literally, this amount of time represents 1/4 of the sine wave. Then we have another 1/4 to get us back down to 0. Then another 1/4 to get us to our negative peak value. Then another 1/4 to get us back to 0 and increasing. So this amount of time from 9.8 milliseconds out to 15.1 milliseconds is our period divided by 4. We know that omega is equal to 2 pi divided by our period, right? So based on this information, our period is going to be 4 times 15.1 milliseconds minus 9.8 milliseconds. So if I put this in my calculator, because I can't do that in my head, the period is 21.2 milliseconds. So if we do 2 pi over 21.2 milliseconds, 21.2 times 10 to the minus 3, we get an angular frequency of 297.7. Hold on. 15.1 minus 9.8 times 4, 21.2. Okay. I must have typed something into this thing wrong when I was getting my answer, but anyway. So 2 pi divided by 21.2 times 10 to the minus 3. Oh, nope. I typed it into my calculator wrong a moment ago. 296.3766. So let's call that 377 radians per second. So this value of omega matches our expected answer as well. Okay. So the last thing we need to do is figure out what our phase angle is going to be. Okay. So we are told that this is a sine wave. So can anybody tell me how much delay our signal has experienced?
Is it 9.8?
It is indeed 9.8 milliseconds, right? So if our signal wasn't delayed at all, or it wasn't advanced, essentially if our phase angle was 0, it would have been 0 and increasing at t is equal to 0. But instead, it's 0 and increasing at 9.8 milliseconds, which means it's been delayed by 9.8 milliseconds. So this amount of time from here to here is our delta t. So our phase angle theta is going to be negative because we know that we are time shifted to the right, so we have a negative phase angle. negative omega times delta t. So that's going to be negative 296.377 radians per second multiplied by 9.8 times 10 to the minus 3 seconds. If I multiply those two numbers together, I'm going to get an angle in radians. I want an angle in degrees because our result was given to us in degrees. So I'm going to multiply this by a conversion factor of 180 degrees per pi radian. And when I put that into my calculator, so let's see, negative times answer times 9.8 times 10 to the minus 3 multiplied by 180 over pi, I get negative 166.41509, so 415 degrees. So putting all of these pieces together, let me do this in green. We have our F naught value, we have our omega value, and we have our theta value. So we have 14.9 sine 296.377 T minus 166.415 degrees is the function. So with only 2 points and the peak value, we were able to mathematically describe this whole thing. Okay, so that is something. As I mentioned a moment ago, I believe this is very similar to a part of one of your homework problems. So when you get to homework set number 19, problem 2, revisit this. All right, before we move on to the last little, actually, no, we'll finish up that last little topic on Monday because I don't know that we have enough time to cover it in the 15 minutes that are remaining. So don't worry about problem 5 from this ICA. We'll look at that on Monday. All right, I know I covered a ridiculous amount of material today, but if you have any questions about anything, I would be more than happy to hang out on Zoom and answer them. If not, I hope you guys have a good rest of your weekend and all of that kind of stuff. Oh, thank you, Zoria. So Zoria asked when the bonus exam is due. So it has been posted. Thank you for reminding me about this. It's due whenever it is convenient for you. So the drop date is today at midnight. So you are gambling to some extent if you don't take it now. That being said, I want you to take it whenever you are comfortable. I would much rather you wait a week or two and really familiarize yourself with the material and secure a very good grade on exam 1 than hurry through it and just try to get some points. But ultimately, it is your decision. So I am perfectly fine with you waiting until the end of the quarter to take it if that's what makes you the most comfortable. But the drop date is today. So, yeah. So if you did pretty well on exam 2 and not so great on exam 1, I personally would stay in the class and just try to crush that bonus thing because it's worth up to 40 points. So that is a huge bump potentially to your exam 1 score. It is 16 questions, each of which are worth 2.5 points. And I think I set the time limit on it for like 4 hours or something ridiculous so that you have plenty of time to get through it. So that is correct, Trevor. So it is up to 40 points added onto your first exam. So your total, no, you cannot go over 105 points. That is exactly what I was about to mention. The best score that I will allow you to receive on exam 1 is a 105. So I don't want you to get like 130 on exam 1 so that you can literally not take exam 3 at all and still somehow make an A in the class or something like that. So the absolute cap is a 105 on any of the tests. Any other questions about anything?